Hello and welcome again to the lectures on state space approach to control system analysis and design. In the last video, we started this LYPUNOV'S stability, and in this too we continue on LYPUNOV'S stability. Today is where we are actually beginning the LYPUNOV'S stability. That previous video was on mathematical foundation essential for learning the LYPUNOV'S stability. So with that mathematical foundation, we are ready to learn the LYPUNOV'S stability. Now we see a few definitions from the classical controls. These are reproduced below in my own language. A system is said to be stable if its output to every bounded input remains bounded. This is that BIBO stability. Bounded input, bounded output stability. The other definition is based on the impulse response. This GT L inverse GS is called as the impulse response. And if this integral of GT taken between the limits 0 and infinity, if this integral is finite, then again the system is stable. However, as I said in introduction in the previous lecture, we are more concerned to learn and to understand stability in the sense of LYPUNOV. So we define stability in the sense of LYPUNOV. The origin of the state space is what we call as stable. So the system is at origin of the state space, and that is stable in the sense of LYPUNOV. We defined a sphere. So we have a spherical region S capital R, and we call its radius as capital R, and there is another spherical region S small r, and its radius is small r. So if we have some initial condition in SR, the sphere S of smaller r radius, and a solution starting with that initial condition from that x0 does not go outside S capital R, the spherical region of capital R radius, as t tends to infinity, then the system will be called as stable. Then the origin of the state space of the dynamical system will be called as stable. So I am assuming that if it is not the origin of the state space where the equilibrium of the system exists, then that has been transformed, and at the point of equilibrium we are considering the origin of the state space. So this is based on a solution starting in a sphere of radius small r, does not go outside, remains confined with the spherical region of radius capital R. Then the system is stable in the sense of LYPUNOV. The origin of the state space is stable in the sense of LYPUNOV. If in addition the solution approaches the origin as t tends to infinity, then this is called as asymptotic stability. So not only it is stable in the sense of LYPUNOV, that means a solution starting somewhere in S small r does not go outside and remains confined in the spherical region S capital R. In addition to that, if it approaches origin of the state space as t tends to infinity, then it will be called as asymptotically stable. It is a stronger condition. This is less stronger condition. And instability, if the solution starting in S small r leaves S capital R, if it goes out, then the origin is called as unstable. All these three definitions are depicted here in this diagram. We have this region, this larger sphere as S capital R, and S small r we have depicted by the smaller sphere, this one. And in that region we are considering a point here, let us say, where the solutions we assume to start. So we see there are four trajectories down. One trajectory is this dash one, this one. It starts here and it comes here at t tending to infinity. So this is a stable trajectory. Why? Because the solution started in S small r. It started within this one, and it did not go outside S capital R. So it is a stable trajectory. This we consider this one, this trajectory. This trajectory starts from the same point. This is just for depiction only. It starts from a point in S small r, and as time increases, it moves at different points, goes outside S small r, goes in S capital R. However, it comes back in S small r. So it is not going outside S capital R. Here it did not come in S small r, here it has come back in S small r. Both these cases are stable situations. This third trajectory, this one shown by this arrow, this type of line, this starts from away from origin. However, as time progresses, at t tending to infinity, it comes to the origin of the state space, and so this is asymptotically stable. So it was the point, it started in S small r, with time increasing, it went out S small r. However, it remained within S capital R, and after doing all that, it came back to the origin. So this is asymptotically stable. In contrary to all this trajectory, this one, it started from some point in S small r, and it went out of S capital R. It did not remain confined, it went out, and so it denotes unstable in the sense of LYPUNOV. This origin for this one unstable in the sense of LYPUNOV. Of course, we have generated all the examples for that starting point only, but from anywhere in this, if it went out, then it is denoting a unstable situation. So now if this radii S small r and S capital R, they become larger and larger. This region, in which here it was shown as a small spherical region, if this expands and expands, becomes bigger and bigger, so as to cover the entire state space, then the stability in the sense of LYPUNOV is global, and in the sense of global stability at large. So stable at large or asymptotically stable at large, these are in the global sense. If that SR is very large, so large that it covers the entire state space. And for the linear systems which are stable, then they are also globally asymptotically stable. This is just a fact I state without any proof or any foundation. Now with this definition, we come to the direct method of stability analysis of LYPUNOV. Direct method of LYPUNOV. It is very old concept. It was suggested in 1892. However, it is in use since 1940s. And this is applicable to both linear as well as non-linear systems, equally applicable. In fact, this is one of the strongest method of stability analysis for non-linear system. The underlying thing in the LYPUNOV stability is the energy concept of classical mechanics. We know that a mechanical system has kinetic energy and potential energy, and if its total energy, that means sum of kinetic energy and potential energy, which is always a positive definite quantity. Energy is a positive definite quantity. If this total energy of a mechanical system is continuously decreasing with time, then this mechanical system will be stable. Now similar is the generalization of the energy concept by LYPUNOV, and there also a generalized energy function called as the LYPUNOV function has been suggested. It is generalization of energy concepts from the classical mechanics. Now we define stability in the neighborhood of the origin. A nonlinear system x dot equal to fx will be asymptotically stable in the neighborhood of the origin if there exists a real scalar function, real and then function v of vector x. It should be continuous and its first order partial derivative should also be continuous. That means del v by del x I equal to 1, 2, etc. So not only the function is continuous, but its first order partial derivatives are also continuous. If such a function exists for the nonlinear system, and if it satisfies this property of being positive definite, this is the definition, that at the origin it has to be 0 and at all other points than the origin it should be non-zero, it should be positive. So if it is continuous with continuous first order partial derivatives, and if it is positive definite, and in addition if its first time derivative v dot is negative definite at all those points other than origin. So if Vx is positive definite, if v dot x is negative definite, and if Vx is continuous with continuous first order partial derivatives, if such a function exists for the nonlinear system, then the system will be stable, then the function will be asymptotically stable in the neighborhood of the origin, and origin is that point of equilibrium of the nonlinear system. So these 3-4 things we have to have a real scalar function for the given system Vx. It should be continuous, its first order partial derivatives should be continuous, it should be positive definite, and its time derivative should be negative definite. Then it is asymptotically stable nonlinear system. we extend the definition to global asymptotic stability, this global. Now, to be globally asymptotically stable, it should satisfy the properties given here, that first of all, it should be continuous, its first order partial derivatives should be continuous, it should be positive definite, and it should be radially unbounded. That means whenever x tends to infinity, Vx also tends to infinity. So if all this happens, and if V dot is positive semi-definite, and of course, V dot is negative semi-definite, and it should satisfy that it should be non-zero along any trajectory of the system except at the origin. So what we have done, that in the previous definition, that V dot x was restricted to be negative definite, but if it is at some point, if it is semi-definite and that point is not on the trajectory of the system, then it should not bother. It should not bother us. So we have taken that condition as some kind of a slight relaxed over the V dot x less than 0. We are allowing V dot x to be semi-definite, negative semi-definite, and we are restricting it to be non-zero only on the trajectory of the system. So if these conditions are satisfied, so first thing is that Vx should be continuous. Second thing is its first order partial derivatives should also be continuous. Third thing is it should be positive definite. Fourth thing is it should be radially unbounded. Fifth thing is these two together, that V dot x is negative semi-definite with the condition that it is negative and it is non-zero on the any point x which is not on the trajectory of the system other than the origin of the state space. Then the system will have the characteristics of global asymptotic stability. So essentially this definition should be identical to the definition of that stability in the neighborhood of the origin. This one is extra in this, that the Vx is radially unbounded. So then the system has global asymptotic stability. We define instability. We have two regions. One is N, it is a spherical region, and within that there is a small region, a part of region N is N1. So we have two regions, a spherical region N denoted by N, and in that a region, not necessarily a spherical region, N1. And in with these two, we have that Lyapunov function Vx satisfying these conditions of being continuous with first order partial derivatives also being continuous in N1. Because N1 is in N, so Vx is continuous and its first order partial derivatives continuous everywhere in N1 and N. And at the boundary of N1, which is inside N, Vx is equal to 0. And also we know that V0 is 0. So obviously the origin will be a boundary point of N1. The origin of the state space has to be necessarily a boundary point of N1, because at the boundary point of N1 inside N, we are assuming Vx to be 0. And at other points in N1 region, Vx is positive. And V dot x is also positive. Meaning that if there is a state in N1 it will grow with time. V dot x being positive, it will grow with time, and so the system, the origin will be unstable. So we are conceptualizing of a region N1 which is inside N, then origin is the boundary point of N1, and in N1 Vx is greater than 0 and V dot x is also greater than 0, then the system is unstable. This is depicted by this diagram. This greenish circle is the region N, and in that this is the region N1 up to there, and we said that origin is on the boundary of N1 and N1 is in N. So this N1 is in N. Now I have shown by hatching, and we have Vx which is 0 at the origin, and this is denoting the Lyapunov function Vx, somewhere it will be. Now this is for Vx equal to 0, this is for Vx equal to K1, K1 is non-zero, this is for Vx equal to K2, K2 greater than K1, both non-zero. So if there is some initial condition x0, with time it will grow, because in this region which is shown hashed, two things are happening. One, Vx is greater than 0. See, it is K1. Subsequently it is K2 and so on. So Vx is greater than 0 in this hatched region, and V dot x, which we said in the previous slide, is also greater than 0. So obviously the x has to grow with time and it will leave the region N, and so the system is unstable. This is the concept of instability. Now just as an application of direct method of Lyapunov, we show an example. We consider this linear system, of course. We are not considering a nonlinear system. I suggest you to see Gopal's book, in which he has given an example of nonlinear system. The same example is also given in the book by Franklin Powell and Imami Naini. So please see that. But to just demonstrate the concept, let us consider this nonlinear system. This linear system. And we have to determine the range of K for stability of the system. Now, as was said, we have to think of a Vx, a Lyapunov function, and here it is the Lyapunov function which is thought of. Now, in fact, I also cannot explain why this Lyapunov function is thought of. One generally thinks of a simple function like x1 square plus x2 square plus x3 square. In this case probably would have been simpler. I'm sorry. But this one, as we will see, is selected carefully so that it gives a solution which is simpler. So we start with this Vx and we differentiate it with respect to time. So this one will give 10k x1 dot. This will give 2k x1 dot x2 and 2k x1 dot by chain rule. This will give 20 into 2, 40 x2 dot, and so on. And then we substitute x1 dot equal to 1 times x2. Similarly, here x1 dot is x2, and like that x2 dot, x3 dot, etc. we substitute, and after that substitution we obtain this expression, and this one eventually simplifies to this one, v dot x equal to 2k minus 40 x2 square. Now we look at Vx and v dot x. Actually, in the beginning itself, we would have analyzed Vx, whether it satisfies the various conditions. Is it continuous? Yes, it is continuous. are its partial derivatives with respect to x1, x2 and x3 continuous? Yes, they satisfy. Now is it positive definite? So let us find out. And is v dot x negative definite? These two we have to analyze. So first, positive definite. How we do? So as I said, that in order to see the positive definiteness of a quadratic form, we can see the matrix R. So in this case, if we make the matrix R x transpose Rx, if Vx is x transpose Rx, then R will be 5k, then 2k x1 x2 will give a k here and a k here, then 20 x2 square will give a 20 here, 8 x2 x3 will give 4 here and 4 here, and x3 square will give 1 here. And these two entries, because there is no x1 x3, so it gives a 0 here and 0 here. So I have carefully made it as a symmetric matrix which is required for R. Now we can see that by applying that Sylvester's theorem, for the positive definiteness of this R, this 5k should be greater than 0 or k should be greater than 0. Then we see that this determinant should be greater than 0, and finally this determinant should be greater than 0. So if we do all that, we get into this condition. 20 k should be within 0 and 20, and then we see that for x equal to 0, if x is identical 0 everywhere, then this Vx becomes 0. So Vx is 0 at x equal to 0, and it is non-zero, it is positive if k is between 0 and 20. And we see that v dot x, it is simpler to analyze. V dot x will be negative if 2k is less than 40 or if k is less than 20. So these two conditions together, Vx should be between 0 and 20 and v dot x should be less than 20. These two together gives the stability condition, which is k should be between 0 and 20. This also you can do it as an exercise. You can determine by Routh's condition that we get the same answer. Routh stability criterion. You can make the Routh-Hurwitz array for this system. You can get the characteristic equation, make the Routh-Hurwitz array, and you can analyze, so you will get the same condition. Now we summarize this video. We saw the definition of stability in the sense of LYPUNOV, and the asymptotic stability and the instability, the three definitions. And we saw the direct method of LYPUNOV for the stability analysis. As I said, in the direct method of LYPUNOV, for the given function, we have to choose a LYPUNOV function with the conditions that it should be continuous, its first order partial derivatives should be continuous, and it should be 0 at the origin, and it should be greater than 0 at all other points where x is non-zero. So Vx has to be found of that type, and for that Vx, the v dot x should be negative, then the system is concluded to be stable. Now getting that kind of a LYPUNOV function is very difficult task. One has to really apply ingenuity to get that Vx. There are methods in literature we are not going to cover in this course that you can do as a self-study, So there are methods in literature for selecting the Lyapunov function for a function for any given dynamical system, linear or nonlinear, for stability analysis of that. But all said and done, it remains true that in order to be able to apply the Lyapunov's direct method of stability analysis, we can face a lot of difficulty in choosing a proper Lyapunov function satisfying those conditions. With that limitation, we sum up this video. Thank you very much. See you again in our next lecture. Thank you.